Trust is one of the most valuable commodities in the world. Without it, the computers and devices we rely on simply cannot operate. This podcast delves inside the concept of trusted computing, looking at the ways standards and specifications can keep you safe from attackers.
Welcome back to Inside Trusted Computing. My name is Thorsten Stremlau, and today we're going to take a closer look at the evolution of the world of trusted hardware. How Trusted Computing Group's DICE specification is bringing hardware trust to billions of devices that can't accommodate a full TPM. Today, I'm joined by someone who knows this much, much better than I do and than most. My guest is Dennis Mattoon. Dennis, thanks for joining us. And could you introduce yourself just briefly?
Cool, thank you. So my name is Dennis Mattoon. I'm with Microsoft. I spent the better part of the last 20 years part of Microsoft research working on things mostly in the area of hardware security. I was one of the founders of the security and privacy research and engineering team at Microsoft Research. And then over the last couple of years, I've moved on and sort of followed some of our technology out of research into product groups inside Microsoft as one of the architects, part of the hardware security team inside ENS. ENS is the enterprise and security team inside Microsoft.
All right. So, Dennis, I'm just going to talk a little bit about evolution and then hand over to you for all the details. But when we take a look at the past decades, obviously computing devices have been shrinking in size and cost and in power draw. In the beginning, we had all these PDAs and rugged handheld computers and all sorts of data terminals. And they weren't glamorous, but they were the first kind of sign that computing didn't just live on desk. And so now, as the evolution comes through it, there's many, many more small devices just about everywhere, from wearables like medical monitors and fitness trackers and IoT sensors and agriculture and all sorts of automotive ECUs and smart hubs, all sorts of different types of things. And these devices have moved from being single purpose, standalone functions to being part of an always connected global ecosystem, right? But as these devices became smaller, the expectations of security also became much, much bigger, right? We wanted strong device identity, attestation. We couldn't really take the power-hungry or costly implementations for this kind of security. And so I guess with the changing security landscape, we also got a changing security solutions landscape, right? And so as IoT devices, for example, in particular, became targets for attacks, even though the TPM helped enormously in the early days. Basically, when you try to drop a TPM into a low-cost sensor or wearable, you quickly run into limits in space, cost, and power budget. And that's basically where the Trusted Computing Group set to fill out this gap with the DICE specification. It's a way of bringing hardware-based trust to devices where full TPM isn't really practical. So, Dennis, could you dig a little bit into what I just said in terms of what DICE is, how it works, and how it's becoming, and it's already is a very important part of the security puzzle, right? And not just for IoT, but anything that needs strong identity or measured boot. Can you talk a little bit about that?
No, absolutely. It's the perfect setup. So, it's been about 10 years ago now. And my team, guy on my team, Dave Wooten, who listeners to this podcast will no doubt be familiar with, was the original editor on, well, not the original, but the last editor on TPM 2.0 at specification. My team in research, along with Dave and some other guys, were responsible for bringing up the original TPM 2.0 reference implementation. So around 2014, we were wrapping up the work on the original TPM 2.0 that was published in, I think, October of that year, or maybe, late 2014. And we were thinking about what's next, like where are things going to go from here? Around that time, IoT was the big thing. TPMs were awesome. They're going to be in every workstation and laptop in the world. But what about the billions of devices that are going to make up this IoT, this Internet of Things? What about those devices? So we set about coming up with methods for providing minimal functionality that could provide for identity and attestation for even the smallest of device. So TPM is great, but compared to what we would refer to as a minimal root of trust, There's lots of stuff in there, lots of commands. It's a big beefy thing meant for big BT workloads. At the time, it was this emerging landscape of IoT, which is much more resource constrained devices. It would be infeasible for every single connected device that we could envision to contain a TPM. So how do we create a minimal set of hardware requirements to enable meaningful security scenarios that include identity and attestation? Because we sort of saw identity and attestation as that baseline requirement, as sort of table stakes for any sort of meaningful security scenario. So October 2014 was the original publication of a project we called Riot. In those days, it stood for robust, reliant, resilient, pick your favorite R word, IoT. And that paper was intended to address this area. And that set forth a set of some hardware principles for any sort of minimal root of trust. At the same time, during the development of the TPM, TPM provides also root of trust functionality for a platform. But one of the things the TPM lacks, and this was intentional at the time, is a root of trust for measurement, an RTM. That first thing that performs the initial set of measurements that your trust chain is sort of rooted in. So the sort of dual purpose for this root of trust project that we were spinning up was not only do we need to address security functionality for tiny devices, but also this could act as the RTM for every device that does contain a TPM. So this sort of minimal root of trust could cover not only the gap in this big picture that we are seeing, but also this entire emerging area in IoT. So not long after that, I think it was 2015, we formed the RTM subgroup inside TCD to start working on this minimal root of trust, which at the time was an RTM. And we started seeing this as being super useful in the IoT space. Not long after we spun this up and brought this hardware specification to TCG, we started to see the promise of this in the IoT space for minimal devices. And this work sort of got promoted into a technology work group inside TCG, and it was renamed DICE because, for obvious reasons, Riot wasn't going to be the winner for the public name because of copyright issues and everything else. So it was renamed. I wasn't there the day they decided on DICE, but that's the name that they came up with, and then so the rest is history, so to speak. Now, the bigger point, though, you also mentioned DICE being prevalent in so many devices today. It's not just the IoT space that DICE was sort of successful, and where in my opinion, it saw even greater success is as a component within a broader, sort of richer set of security, bits. It's positioned as a complement to TPM-based solutions, is where it saw the most adoption. So we were sort of caught off guard. In fact, we thought this is going to be a big deal for IoT because all these devices are going to be connected out there, and they're going to need to have some sort of meaningful security guarantees. It worked, except where we saw the greatest uptake was in what today is referred to as an integrated root of trust, an IROT. So DICE acting as an integrated root of trust in beefier solutions that include a TPM. That's where we have seen the most uptake, and that's where that's the sort of hot area of development.
So what's the absolute minimum hardware requirements for a device to implement DICE? Is that something that you could cover?
So I referred to that earlier, right? The minimal set of hardware requirements in order to get this off the ground. That's embodied in what's referred to as the DICE hardware specification. That is some kind of statistically unique device secret possessed by the device. And that is instructions on the device, or the root of trust, let's call it, on the device, that is the only thing allowed to view that secret. So you have this minimal RTM, essentially root of trust on the device, usually in ROM, but it can be anywhere that sort of satisfies the hardware requirements of immutability or updatability by a manufacturer controlled process. That minimal RTM, that DICE, is the only thing on the platform with access to the unique device secret. It will measure the next software component that it's going to load on the platform, or firmware component, the next thing it's going to pass control to. It combines cryptographically the unique device secret on that device with its measurement of what we refer to as layered 0, that next thing that the DICE is going to pass control to. Combines that to form what's referred to as a CDI, a compound device identifier. And that's passed on to that next piece of software or firmware as a secret value. And now from the reference point of that next layer, the same process plays out again. That's the next layer's secret. That next layer measures, in turn, the layer it's going to load, combines those two elements cryptographically to form the next layer secret, et cetera, all the way down the chain. And this is interesting and valuable because you are now creating a linkage between the identity of the firmware running on the device and that unique device itself. And this can be leveraged in lots of different ways. There's a bunch of different specs from TCG on different attestation scenarios and different deployment patterns for how these things can come together in meaningful ways. And sort of that's like the essence of how this comes together.
And then, and again, from an engineering perspective, what kind of performance or power impact should a designer expect when implementing DICE on a low-cost microcontroller? You know?
So back when this sort of thing was first getting off the ground, we were helping out various system partners of ours with adoption of this kind of thing. We were finding that lots of tiny devices in the MCU space and small SoCs were already doing some version of this out of the box. Few devices needed to have any sort of big hardware changes because lots of devices take similar approaches already. But up until the point of DICE, they'd not done a good job of formalizing this sort of methodology, this kind of abstraction. So to your point, usually very little impact on performance and especially hardware designs, just because people were already kind of nibbling around the edges of this kind of solution. And even when it comes to handling secrets, before DPE, which we can get to, before DICE, firmware is already responsible for handling secrets. There's already sensitive stuff happening way down at those lowest levels in ROM, and then that first layer or two after ROM. The specifications like DICE and the various architecture specifications just sort of formalize the methodologies around doing this. So even if you don't migrate to a solution like DPE, a DICE protection environment, you're still better off because you're taking more care and following a standard practice around handling those secrets inside firmware.
So Dennis, does that mean that through a firmware update, theoretically, if my device, if my sensor, my MCU met the minimum hardware requirements, I could actually upgrade it to DICE even if it's already in the field through a firmware update?
Absolutely, yes. Provided, of course, that the hardware you're updating already follows the spec, except the spec is a set of principles more than it is a bunch of checkboxes, right? So as long as your hardware is within the sort of boundaries of the DICE hardware specification, absolutely, yes, you could put together a firmware update and push that down to the device and adopt this for sure. One thing I failed to sort of highlight explicitly earlier, though, and you just reminded me of it, was because of the sort of DICE model for putting together this chain of trust. So because each layer, that secret is dependent on the secret that came before it, and steal secrets to those secrets that it's been handed. An update to the device after you've adopted a DICE model also means that secrets are protected just by virtue of updating. So, for example, say that layer 0 had some kind of exploitable flaw, and before or even after this flaw was exploited, you recognize this and push an update to the device. Because the measurement of that layer 0 firmware was part of the secret, that secret was used to derive a key, that key was used to protect secrets on the device, updating automatically rekeys the device in that case, because you've changed the firmware that went into the measurement.
Yep.
The measurement that led to the key is different, so now that key is different. If I manage to persist and exploit in that layer 0, the next thing that happens on reboot is I get a key, except that key is by definition not the one that I want, because I, as the attacker, just made a change to layer 0. I now can't get the original key. As soon as I persist that attack, I'm now unable to achieve my goal. And that's sort of one of the values of the DICE model.
Very, very good. So we're going to move ahead now. One of the areas that we've seen DICE being implemented is, for example, OCP's Calyptra. And we're covering how TCG works with standards bodies and open source in a separate blog as well. How important is open source and I guess for DICE and how important is it for open source hardware initiatives to adopt DICE as a trust anchor?
I've not seen a lot of standards out there that address this space specifically. So I say for DICE in particular, I think it's pretty important, just because as you can imagine, hardware vendors, they want to have some special sauce. They want to have some differentiator. They want to have something that makes their platform unique and interesting and important, but they still care about standards. And that's sort of the valuable thing, So especially with collaborations like with OCP, especially in data center kind of application where trust of the customer in the CSP, in the cloud service provider is very important. Open standards, in my opinion, are critical for this environment, because I need to have some assurance that my most important of workloads running in your data center are going to be resilient to attack and secure. And I would love it also if I could remove the trust dependency I have on, for example, the administrator or the supply chain that wanted to provide the box. So yeah, I think it's pretty important.
Earlier, you also mentioned DPE. What is DPE and what's driving that evolution?
This is one of the reasons I'm so thankful for that sort of collaboration with OCP, because it's one of those situations where an organization or set of companies saw value in what you were doing, and in a lot of ways sort of validated the ideas that we had in the first place, and in some ways challenged those ideas to take them farther, right? What's that next thing we could be doing? We have this awesome architecture. What could we do to make it even better and to adapt it to even more kinds of environments? And sort of DPE is kind of that evolution in some ways. So we talked about what DICE is. It's sort of an extension of firmware and a collection of hardware requirements for devices. And in that kind of environment, you're still better off with DICE specs and that kind of architecture for various reasons, which we already talked about. But what if I wanted to take handling of secrets out of my firmware altogether? I don't want my firmware to be in possession of sensitive information. I want to find somewhere to put this stuff during boot and runtime so that it's protected. And at first, that sounds an awful lot like a TPM. We could say, well, just throw a TPM on there. Except, again, when talking about one, that's also sometimes infeasible and just a difficult engineering project. So say you have some SoC, and I want to, on that SoC, integrate a root of trust. I don't want a discrete part on there. I don't want a separate bus to have to talk over. I want that extra complexity, but I want to be able to have the benefits of DICE without the downsides of a discrete part. So that's where an integrated root of trust comes in, an IROT comes in, and that's essentially DPE. So DPE stands for DICE Protection Environment, and it is a isolated space in which DICE operations and secrets are carried out and held. So rather than firmware itself doing those cryptographic transformations on secrets, rather than the firmware itself performing the measurements of the next loaded component and deriving keys and certificates, creating certificates also. TCG provides a specification called DPE, the DICE Protection Environment, that is responsible for performing those operations and for maintaining the isolation of those secrets and protection of those secrets. So firmware never has to wield a key. Firmware never has to be in possession of a measurement. These are things that to be maintained by the DP.
So I have one last question for you, Dennis. By the way, really exciting. And also, I guess, being able to look at the evolution and the applicability of this. So one last question is, if I'm a product designer today, what would be the best starting point for me to understand and adopt DICE, let's say, in my next project?
So I think the best thing people can do is become part of TCG. Every week we've got a DICE work group call. We're always welcoming and looking for new and active members. For me, adoption and sort of understanding and seeing how these things apply in new and interesting ways is always best done just being able to talk to the experts on the subject. And you can do that by becoming a TCG member. I have a long to-do list for DICE intro material, guidance documents, frequently asked questions, these kinds of things. Because we get all kinds of questions on exactly this area. And we just never seem to take off those items on our to-do list, actually producing these nice guidance documents or references. There are resources out there. There's a GitHub out there with the original Riot reference. We have our early reference documents are still available publicly around device attestation and identity that sort of explains the principles that we talked about today. the best possible way to hit the ground running is to become part of CCG, go get on a DICE workgroup call and we can have a conversation about it.
So Dennis, thank you so much for walking us through this. You've made it very, very clear that DICE is enabling secure foundations for devices that really previously had no path to hardware trust or had fragmented or non-standard paths. And so as the world becomes more connected, and these trust anchors are critical to defending against the threat landscape. So thank you again, Dennis, for everything that you said.
Absolutely. Thank you.
That's it for this episode of Inside Trusted Computing. And this is also the last episode in this series. I hope that we've been able to show you how trusted hardware and open standards are securing our connected future and our current devices. And until the next series, stay safe and stay secure.